Come on in, everybody. Feel free to ask me any questions before we start. We got about 2 minutes, not a whole lot of time, but we do have 2 minutes, so you can ask me if you need.
Hello, Professor.
Hello, how you doing?
Hi, this is Alyssa Oliphant.
Yes, ma'am. How can I help you?
Hi, I spoke with you at the end of class last Monday. I sent you an email again a couple hours ago about the extending the assignments that were due Sunday night.
Right.
When I tried to attempt to do them yesterday, yes, I saw they were still locked. So I was like, maybe you didn't unlock them yet.
Which chapter was that? Refresh my memory if you don't mind. I'll look at them right now.
I took a picture of it. I'm sorry. It was chapter 8. The test was of 5 and 6.
Okay. So I'm looking at chapter 8. It said chapter 8, conceptual. Neither one of them are due yet. Oh,
They're
you're
not
talking about the chapter 8, the test.
Yeah.
Okay, gotcha.
Yeah, the homeworks were due at midnight Sunday, and then the practice test and online test, chapter 5 and 6 was due.
All right, let me check that real quick while we're here. So that works there. And now I'm going to get back here and let's see. Today's the 18th. Okay, so I got that worked out. Now let me look at the. And you were talking chapter 7 and 8 test.
I'm sorry, what was the question?
I said, you were talking about 7 and 8 tests because the chapter homework's not anywhere near due yet, but.
No, 5 and 6,
Okay.
if
And
that's what
that's
it says online.
the practice test for 5 and 6. Gotcha. And the regular test for 5 and 6. All right.
The practice test and the online.
All right. I'm going to change that to, I'll take the practice test. Let's see. Oliphant. And I got that. Anybody else here that might need a couple more days to do that? Looks like we're pretty good.
Did I also get that?
Yeah. Susan, what's your
I
last
don't know
name?
if I've done mine.
What's
But
your
I
last
probably have. The test. I just realized, like, I just checked. I haven't been checking my stuff. I just checked and I realized that I need to do that test. Can I do the test after
Gotcha.
class?
Yeah, let me look and see who it is. See if I put your name up here. It's Josh Curry.
Yes, that's me.
Okay. I've now got an exception for you on the practice test, and we'll do the same thing for the regular test, and then you'll be good. And I'll give you till Sunday. That cool?
Thank you.
Okay. Thank you so much, Professor.
Sorry about the delay on getting that done.
It's okay. I just wanted to make sure I didn't miss it again.
Yeah, that's a good. It's good to keep on me. I got so many things going on. There's no telling what's going to happen.
Yeah, I understand.
But thank you very much. Anybody else have any other questions? About anything? Okay. I got both of those done. Got that done. All right. So now the test is available for you to, if anybody else needs it, just send me an email. Actually, send me a text message right after class. That'd be the most reliable way to make sure I get it, I see it, and do it. So, got another person coming in. All right. So it's now about 3 minutes after. We've got about 10 of you in here. That's not too bad. It's a little smaller than I'd like, but it's enough to get started. So again, I ask one more time. Anybody have any last minute questions? All right. Well, I'm going to go ahead and share my screen. And in this case, I'm sharing the screen and I'm going to do a little bit of stuff to finish up chapter 7, which was conservation of energy, or excuse me, chapter 8, which was conservation of energy. Just a couple little things that I didn't really mention and I wanted to mention really quickly. Some of it's fairly generic, but other parts of it's very specific. And I'll start off, well, as soon as this actually opens up, I'll start off with some considerations of stuff from chapter 8 that we hadn't really covered. One thing is, power. I need to discuss power and escape velocity. So I'll start off with the escape velocity scenario. So, from conservation of energy, we use the version that is initial potential energy plus initial kinetic energy plus work in to the system is equal to final potential energy plus final kinetic energy plus work out, plus I add a term E loss for, work done against friction or basically energy stolen due to friction, air resistance, that kind of stuff, so on and so forth. What I want you guys to imagine is Thor or Superman or somebody is going to take a spaceship and give it such a fast throw from the surface of the Earth that it's going to go so fast it completely escapes the gravitational well that is the Earth and leaves the surface of the Earth with such a high speed that it'll just reach infinity with no energy left over, so that it'll actually just reach infinity and come to a stop. So I don't want any extra kinetic energy left over. But I'm also going to imagine that it's a scenario in which the air resistance due to the atmosphere is negligible or zero. I'm not doing any energy loss. I'm not taking into account how much work Thor or Superman or anything like that has to put into it. So really what that gives me is a initial potential energy from Newton's law of gravity of negative G times the mass of this rocket ship that Thor is throwing times the mass of the Earth. And of course, you could do this for any planet and just replace the subscript if you wanted. All that divided by the radius of the Earth. Notice the negative sign. This is the only time that any of these terms in the conservation of energy equations should actually equal zero, unless you do something weird like create the zero of potential energy above some position or above some height that you get during the problem. If you do that, then yeah, you're going to get some negative terms. But other than that, everything's going to be positive except for this guy. Now, that's the potential energy. We also have a kinetic energy given by, assuming it's not relativistic speed, 1/2 m times what we call this velocity is the escape velocity. So the velocity at which Thor or Superman could throw a projectile, i.e. a spaceship that we're in, okay, such that it just reaches infinitely far away and comes to a stop, is called the escape velocity. As I said, we're assuming the work in is zero. The final potential energy, because R is going to infinity, the negative G m over R is zero. Again, I'm going to say it's going to just come to a rest as it reaches infinity. So the final kinetic energy will be zero. The work out is zero and the E loss is zero because we assumed that. So when I go to solve this, for one thing you see is that the mass is in both of the terms that exist. So I could divide out the mass of the projectile, spaceship, whatever you want to call it. And from that, I can get that the escape velocity is equal to the square root of 2 times G times the mass of Earth over the radius of the Earth, and then the square root of all that. That's the escape velocity. And it turns out, if you do this calculation, that's about 11.2 kilometers per second. So that's a pretty high speed, but I want to let you know that that is actually a ballpark speed of how fast planets, comets, things of that sort travel around our sun in our solar system, at least when they're in the inner solar system. Obviously, if Halley's Comet gets out, 20, 30, 40 astronomical units out there, its speed might be quite a bit lower. But in general, the speeds of the planets, Mercury, Venus, Earth, Mars, Jupiter, comets, asteroids, even out to Pluto, is on the order of about 10 kilometers per second. So that's pretty fast. That's the escape velocity, and I'll circle it off. So that's just something that's useful to figure out how to do. If you were taking the astronomy class, we'd also get you to work out exactly what velocity you have to make a circular orbit, what velocity you have to make an elliptical orbit, what's the smallest velocity you could have and still get an elliptical orbit. That would be one smaller than the circular orbit, that kind of thing. But another thing we could do is we could figure out what is, or another way of saying this is, how much faster is the Earth's escape velocity than the moon's escape velocity. So I could put subscript E and subscript M here. So if you want to know how many times faster you have to go to escape the Earth compared to the escape velocity of the moon, then one way of computing that is divide the escape velocity of the Earth by the escape velocity of the moon. And when you do that, you can look up at the equation we got, and you'd see that, in fact, the V escape for the Earth is 2g mass of the Earth over radius of the Earth. And then we're going to divide that by 2g, the mass of the moon, divided by the radius of the moon. Obviously, there's some cancellations there. This 2 cancels out with this 2. This g cancels out with this g. And what ultimately happens, of course, is we end up getting the mass of the Earth on top multiplied by the radius of the moon divided by the mass of the moon divided by the radius of the Earth. And that's the actual symbolic expression of the ratio. And if you compute that, you'll get about 4.7. So that tells us that the escape velocity of the Earth, which is about 11.2 kilometers per second, is in fact almost 5 times bigger than the escape velocity for the moon. And you can, of course, do this for other planets just by substituting the mass of the moon for the mass of the moon for the mass of Mars, and the radius of the moon with the mass of with the radius of the moon, so on and so forth. But that's just one other thing I wanted to do. That is employing that that potential energy for the Earth. So anybody have any questions on that? Anything that bothers you about it? Okay, so that is one of the topics that was actually just sort of skipped in chapter 8. Another one is power, and I don't need to do too much with power, specifically because I want you to think of power as the amount of work done divided by the time taken. But I want you to be really, really loose with that. So yes, it's the work done divided by the time taken on average. But if you really want the power at any instant, it's just like we had before. The change in the position divided by the change in time was the average velocity. So the instantaneous rate of work with respect to time is the derivative of W with respect to T, just like the instantaneous velocity is the derivative of X with respect to T. So we could say P on average is work done divided by time taken but it can also be change in potential energy over change in time. It could be change in kinetic energy over the time taken, all sorts of stuff. So that's what I mean by I want you to be a little loose with this, is realize that sometimes when you're wanting to calculate power, you can think of the work done as really the change in kinetic energy, because that's the work energy theorem. Or the work done is the work done in changing the potential energy. So the change in potential energy is the same thing as the work done. Or you can just think of it as the work done. But either way, you ultimately get that the instantaneous power is dW over dt. So that's an important equation. That's essentially the definition of it. This is conceptually what you want to think. Also, whenever we introduce something, we always want to bring in the units. So I'm going to say power unit wise is clearly the units of work, which are joules, divided by the units of time, which is the second. And I will tell you that that is in fact defined to be the watt. So I've made mention before that a joule is about as much energy as it takes to make a nice, really succulent, red, delicious apple, like you might find in the months of June or July in your grocery store. And you pick it up off the ground and lift it to the top of a dining room table, for instance. That's 1 joule of work. So if you think about a watt, you could say if I did that with an apple every second, then the power that I would have to expend would be 1 joule per second, which is 1 watt. So lifting a red delicious apple from ground to floor, from ground to the top of a dining room table once every second is 1 watt. If I wanted 100 watts, like a 100-watt light bulb, then I'd do 100 apples per second, and so on and so forth. I will also tell you that I think, let me look this up. I want to say 1 horsepower is 746 watts. So let me give you that too. So 1 horsepower is equal to 746 watts. So that makes a crossover. We're generally just going to use units of watts, but occasionally to be a real, a real life citizen living in this world, it might be helpful for us to understand what a horsepower is. And you can see that basically a 1 horsepower is about the amount of work required to lift 746 red delicious apples from the floor to the top of a dining room table every second. So that's a pretty extensive amount of work. If we use the dWdt form, though, I can get something that will become helpful. And you'll see when you look at the examples in chapter 8, you'll see exactly what I'm talking about. But power is equal to dW over dt gives me, since we remembered that work is equal to the integral of f dot dl, you might think that dW could be f dot dl over dt, which if the force is constant, then this is definitely going to be the case, and you'd get f dotted with dl dt. Now, does anybody have any idea what dl dt might be? If you don't, think about the units, but anybody? Open up my chat just to make sure that you guys are seeing that. There it is. Okay, so no one's chatted anything. So dLdt, notice that's a differential length divided by a differential time. So I think you'll recognize that as a velocity. And in fact, one of the formulas for power is if you have a constant force applied to something to maintain a velocity v, then the power expended by that object is force dotted with the v. So in other words, you just take the component of force that's parallel to the velocity and you multiply those two, and that'll give you the work done. So for instance, your book takes the time to give you an example of a car going up a 10-degree hill. If you drew a free body diagram for that 10-degree hill, what you'd find is that the forces acting on it, ignoring air resistance and stuff like that, you'd basically have a normal force, you'd have the weight of gravity, then you'd have, of course, the force that the earth, or specifically the road, is applying to the tires, and that force is actually causing the tires to be allowed to roll forward. That force is acting up the incline, and of course you could break the weight down into components perpendicular and parallel to the incline. So that force that's trying to make the tires spin out, but because the Newton's third law is applied to the tire, to the force between the road and the tire, that force is pushing the car up the incline, and it's fighting the component of weight down the incline, which is mg sine theta. If you want to add to that, as your book does, 700 newtons, say, of drag force, that's the force due to air resistance, then you realize the total force that the car has to supply is mg sine theta plus 700 newtons. That's going to be a constant force as long as you're going up a constant 10-degree slope hill. So yeah, you can just take that force and multiply it by the velocity, and that'll give you the power. And it does some other ways as well. So definitely check out those examples in the chapter. Actually, I'll go ahead and list what those chapters are, or excuse me, what those examples are. I'll say see examples, and I think it's example plural, but let me double check. Yeah. (8-14) and 8-15. These are really fairly trivial examples. They're plug and chug sort of things. So I'm just leaving it up to you to check them out. And that's pretty much it. I think I'm remembering the number right with horsepower. Now, the last thing I wanted to cover, in addition to this, by the way, your book does cover slingshot, or basically gravitational assist. So if you have an object in orbit, for instance, if you wanted to take the Voyager spacecraft that we sent out in the 1970s, that went around a lot of planets because we were using it to do a lot of discovery on various planets. But at certain points, it could, come by a planet, get real close, and then go away. That was helpful in that we could see, close-up pictures of that planet and learn stuff about it. But it's also helpful in that if you imagine what's going on, you'd have a spacecraft that's moving at some speed that you accounted for and planned it to have, but it's coming somewhat towards, let's say, Jupiter. Well, Jupiter has a gravitational pull on it, and therefore speeds it up, and then it gets around Jupiter and gets slung around with a higher speed than it had before. In that sense, you're using conservation of energy to create a slingshot. That's a very interesting thing, and you can work it out in terms of conservation of energy and get an idea how fast it'll go. But you can also do it in terms of conservation of momentum and work it out that way, which you'll see in the next chapter. The main thing is I want you to know about that, and I hope you read about it. And I don't think I did put any problems in it on the homework, but I know I won't give you any problems on it on the test. So it's not something that I'm going to test you on, but it is something that I find interesting and that I hope you take the time to read. So that's one other thing. Now, the final thing that I want to do with chapter 8 is I wanted to talk to you about potential energy diagrams. Specifically, potential energy diagrams tell us something about the way things behave. So I want you to look at this potential energy diagram. So I'm going to draw a vertical axis, and then I'm going to draw a horizontal axis. And I'm going to say that the vertical axis is U, the potential energy. And we're going to assume this is like a one-dimensional potential energy. So the horizontal axis is just X. Now, the graph here might do something like this. Okay, so all of that is and I'm trying to make sure this this curve isn't exactly vertical right here on the right side of that deepest well. Let me make sure that's not the case, because we obviously need it to be in some sense a function. So hopefully we can do that. So I got that one. Now I'm going to do black like this. Okay, so what I want you to do is just imagine this is a potential u of x. And remember the theorem that we learned about. There's basically, if one of these things is true, then all of them is true. And one of them is that F is a conservative force. And what F is a conservative force gets you, among other things, is that there exists a scalar function that can represent the force such that F is equal to the negative gradient of U. And if you reduce that to one dimension, this is going to be partial of U with respect to X times I hat plus the partial of U with respect to Y times J hat plus the partial of U with respect to Z K hat, like that. And notice the negative in front of it. So in 1D, this becomes F sub X is equal to negative du dx, like that. So now that we have that background, I'm going to put out little red dots to represent extrema of the function. So here's an extrema, there's an extrema, there's an extrema, there's one there, that sort of thing. So I will say everywhere the slope of u of x is 0 creates an extrema. Which can be a maxima, a maxima, a minima, or a point of inflection. That's mathematically what's going on. But more importantly, I want you to know what's physically going on. Given that the slope is 0, can anybody tell me what we can figure out about the force?
It's changing direction.
Sorta. I mean, that's actually you're hitting something and you're getting really close. But look at the stuff that I wrote in black down below and see if you can give me a more even more specific answer. And anybody for that matter. But yeah, you're somewhat right with what you said. So how do you, in calculus, how do you calculate the slope of a function? I'm sure y'all know this.
Take the derivative or rise over run, however you want to look at it.
Exactly. So you take the derivative and notice that the derivative, at least the negative of it, is the force. So if the slope is 0, that means F is equal to 0, which means it's in equilibrium. Okay, which I'm going to abbreviate because I can never remember if that's got 2 L's or 14 of them. But anyways, so each one of these points that I've made a red dot on is actually an equilibrium point where the force is equal to 0. But there's equilibrium points and then there's equilibrium points. So for instance, if I take this little point right here and apply just a small force to that red dot to the right, so it turns out that you can analyze what's going to happen by pretending this graph is actually like a surface made out of plywood. So instead of thinking of that as just a graph, imagine it's almost like a quarter pipe with, valleys and all sorts of stuff like that and crests. And what you'd see is that's sort of the bottom of a quarter pipe or a bowl or something like that. So if I give that little red ball a push to the right, what's going to happen to that little red ball in that plywood valley? So you see the little red dot I drew, and then I put a little blue arrow next to it. So I'm imagining putting a ball down at the bottom of a well made out of plywood, a well surface. And at the very bottom is the ball, and I give it just a slight push to the right. What's going to happen to it after I give it that slight push? Do you see that if I push it to the right, it's just going to come back to the left? Because the steepness of that plywood right there is going to make it come back. Similarly, if I push it to the left, it's going to be pushed back to the right. That's the same thing that happens right here as well. So what we say is these two minima are points of stable equilibrium. And what I mean by that is stable equilibrium is the type of equilibrium where you can give it a little perturbation or a little push in one way or the other, and it corrects itself by coming back. Yes, thanks, Monica. Now, if you look at this point over here, that point is a maxima. And that implies it's unstable equilibrium. Oops, left out the L. Okay. And then this point right here, the point of inflection is neither. Meaning there could be conditions where if you give it a push to the right, it's going to come back. But it might come back so strong that it ends up taking off to the left, or it might just come back and settle where it was, so on and so forth. So that's the key to the potential energy graphs is you can look at potential energy graphs and actually imagine them like they're a surface, a walking surface. And anywhere that you can imagine giving it a little push to the left or to the right, actually in every possible direction, if it restores itself, if it has a restorative quality, then it's stable. If it doesn't have a restorative quality, it's unstable. So that was it. That's the last part that I wanted to talk about. So this completes chapter 8. All right. Any questions on that before we move on to chapter 9? All right, so let's jump to chapter 9 then. So we're going to start off with chapter 9, and chapter 9 is about linear momentum, and it gives us an opportunity to think again exactly what Newton said in his Principia. And it turns out that remember, vectors were invented in the mid, maybe slightly earlier than mid 1800s, and more or less was complete by the 1860s, 1870s. There's still work to be done, but the main thing is that was when vectors and vector calculus and vector algebra and tensors and all that stuff came into play. That didn't exist in the time of Newton, so he didn't have vectors. But he understood the importance of things having both a magnitude and direction. So you can imagine that as Principia would say something along the lines of an object of mass m will receive an acceleration a that is parallel to the net external force, and its magnitude is given by the net external force divided by the mass. Or it might say the acceleration is directly proportional to the net external force and inversely proportional to the mass. But again, by stating it's parallel to the net external force and then giving a way to calculate its magnitude, it's essentially given us the same thing as a vector. Now, the Principia in reality said something more along the lines of this. I'm going to use the same notation I used when I covered Newton's second law. So you'll still see the summation symbol, the sigma, the summation of the forces. And the idea of Newton is actually equal to the instantaneous rate of change of a quantity that is mass times velocity. And I'm putting the vector symbols here. Again, Newton would not have had those vector symbols. But the main thing is this quantity down here, this m times v. If you're talking about a single particle, it's the particle's momentum, and it's given the symbol P, is defined to be m times v. And again, that's classical, just like 1/2 mv squared is classical potential energy. There's other equations for it when we get into special relativity and general relativity. But you can look at this and say, well, how does this have anything to do with F equals ma? Well, if you use the product rule, then you could say that this is going to be dm dt times v plus m times dv dt. This right here is what we're used to. This is m times a, which you can see is only a special case in the event that the m does not change as a function of time. So this dm dt really matters. And in fact, you can look at this as the rocket equation. So the summation of the forces is equal to dm dt times v plus m dv dt is called the rocket equation. And I'm not really going to spend any time on it. If you actually go into aeronautical engineering or just space travel in general and want to do that with your physics degree or something, then by all means you want to study this, and you will get plenty of time to play with this equation. But and your book does a good job in specifically showing you how to apply this equation. And the author actually gives us one problem that I seem to recall I did put in the chapter 9 homework. So you get a chance to actually experience it on a homework problem, but I'm not going to test you on it. So I won't give you any test problems on this, but I just want you to know it's called the rocket equation. And the reason that you have to deal with it is because if you've seen any space shuttles or rockets take off, you'll know that the space shuttle is often attached to a really big cylindrical pointy object. And that big cylindrical pointy object has two other big cylindrical pointy objects on each side, one on each side. And all of those are just basically fuel tanks with rocket boosters. So you can see, in fact, that the vast majority of the weight of the ship that takes off from the Earth with our space shuttle or our rocket is almost all fuel. So you might imagine that the mass changing is a very important thing, and it is. And in fact, that's exactly why I was telling you some time ago about if you happen to find yourself on a perfectly smooth, frictionless frozen lake, since it's frictionless, there's literally no way you can walk on it, because if you try to walk, you're going to push backwards, and there's no friction to respond and allow your foot to stop sliding and go forward, or allowing your body to go forward. So you're not going to be able to move. if you're in that sort of situation, which is not unlike the situation that George Clooney's character found himself in outer space when he got cut off from his spacecraft in outer space. But basically, you're stuck somewhere and you have no means of propulsion. So there's nothing that the George Clooney character could have done. And if you really were on a truly 100% frictionless frozen lake, there's nothing you can do in terms of walking and stuff like that. But you could, for instance, let's say, take off your hat. And if you take off your hat and you look in the distance and see which direction you want to go, then you turn 180 degrees and throw your hat that direction. What's going to happen is it requires a certain amount of force for you to apply to that hat in order to make it accelerate. And according to Newton's second law, when you apply that force to that hat, the hat's going to apply the exact same force to you, but in the opposite direction. So you will get, because you weigh so much more than the hat, a very, very, very small acceleration towards the place you want to go, while the hat gets a pretty extensive acceleration in the opposite direction. So then you could just wait out over time, because a small acceleration with literally zero friction will eventually get you where you're wanting to go. So when you do that, you can actually, in some sense, use it to maneuver across it. But see that you're sort of have to bring a hat with you, or a coat, or some shoes, or something like that. Well, if you're in outer space and you want to do that, what are you going to throw? If you're in a spacesuit, for instance, there's not really anything you can pull off your body, because you'd have to pull it out of your spacesuit, which is, sealed. You might have some stuff hanging on the outside of your spaceship, the spacesuit, that you can throw. That would be fine. Or you might have a jetpack of some sort. But the big thing is a jetpack or a rocket ship with rocket boosters. All those things have to pack all the things they're going to throw. And what they do is they take solid rocket fuel, and that causes a little explosion, which makes the small low mass particles have an extremely high speed. That extremely high speed means the force could be a little bit bigger than if it had just been a regular high speed, or even bigger than if it had been just a low speed. So you will get a bigger force out of it than if you just barely thrown it, but you're still going to get a way smaller force than you need for an appreciable acceleration of a big heavy spacecraft. So you have to make up for that by throwing a butt ton of them. So yes, you have to carry a butt ton of individual molecules of fuel to get you to go. All right. So hopefully that helps you understand a little bit where the DMDT comes from, and also helps you understand the science of how we would propel in outer space. We have to shoot things opposite directions to the way we want to go in order to travel there. Now, in addition to that, you can use Newton's second law, as I've told you before, not only for a single object like a baseball. A baseball has a mass. You throw it therefore has a velocity. Therefore, you multiply the mass times the velocity, you get a momentum. And how do you think the momentum is related to the velocity in terms of direction? Anybody have an idea, given that P is equal to mv? Do you know anything about what happens to a vector when you multiply it by a scalar?
It can change direction or magnitude.
You can change direction, but it's a very specific type of change of direction. And how do you do that? By multiplying the vector by a scalar. Do you know? But thank you for answering. I appreciate that. So it
Just
go ahead. I'm sorry.
multiply it by the negative.
Exactly. If the scalar is a negative, then you'll take the vector that was, say, pointing that way. Now all of a sudden it's going to be pointing 180 degrees from the direction it was. However, if the scalar is not a negative, you don't change the direction at all. And guess what? Mass can't be negative. So it turns out that momentum and velocity are always parallel. So P is parallel to V because M is greater than 0. Okay. There are particles, by the way, that have a mass of 0. The one we know exists for sure is the photon, the particle that carries light. That has a mass of 0, but oddly enough, it does not have a momentum of 0. In fact, the momentum turns out to be Planck's constant divided by its wavelength, which is a whole nother weird thing. But anyways, they have momentum too, and then you have to account for that relativistically as well. So there's all sorts of neat stuff that you'll learn about that. So yes, the F equals ma does apply to a single object, and yes, momentum is parallel to velocity. But you can also use F equals ma, or in this case, F equals dp/dt, the instantaneous rate of change of momentum. You can use that version of Newton's second law to apply it to a system of particles as well. So for instance, you might have a car, say, whose mass is 1,000 kilograms, and it might have a velocity of v1 equals 20.0 meters per second. And then it might actually run into another vehicle that has a mass of 2,000 kilograms, but is actually traveling, let's say, north with a velocity v2 of 30 meters per second. And they're going to collide. And in fact, we can go ahead and make up our own coordinate system like so. And we'll say that's the positive x direction, that's the positive y direction. So we'd say our system is defined by M1 and M2, and we would have P1 is equal to 2.0 times 10 to the 4, actually 2.00 times 10 to the 4 kilograms meters per second, which hopefully you'll see that that's the unit that we have, and that points in the I-hat direction. Similarly, we have P2, which would be 2 times 3 is 6, so it'd be 6 point, and let's make this 30.0 just to have it nice and neat. Now I'll go back and try to fix what I screwed up with that eraser. Oops, that was not what I meant to do. So I'm going to do this now and say that's 30.0 meters per second. And now I can say that this is 6.00 times 10 to the 4th kilograms meters per second. And this time it's in the j-hat direction. So in fact, P initial, which is for the whole system, is actually 2.00 times 10 to the 4th kilograms meters per second I-hat plus 6.00 times 10 to the 4th kilograms meters per second j-hat. So that's the momentum before the collision. So that's how you could actually use F equals ma, or in this case, F equals dp/dt for a system of particles. In this case, we had a system of actual 2 cars. You could do it for any number of cars, but more specifically, this is the one for 2 cars. Now, I will show you something else that's kind of neat. So if we look again at Newton's second law, the summation of the forces is equal to dp dt. So we say, what if the net force, and I should say net external force, because I want to remind you, in a case like we were just looking at where we had two cars that we were treating as our system. Those two cars are getting ready to run into each other. And when they do, that's going to be a butt ton of forces from car one on car two and from car two on car one. But those are internal forces. That's a force from one part of the system acting on another part of the system and has no business being on the left-hand side of Newton's second law. So again, I just wanted to point that out, that we're talking about external forces on the left-hand side of Newton's second law. So what if the net external force is 0? Well, the summation forces equals 0 implies that 0 is equal to dp dt. And what's it mean when a function has a derivative equal to 0? Really not liking my writing today. Anyone? What does it mean when the derivative of a function is 0?
The function is a constant.
Exactly. And in this case, it's a constant, but it's also a vector function, which means it has a constant magnitude and direction. Okay. That is the law of conservation of momentum. So momentum is conserved specifically in cases where the net external force acting on the system is 0. So we can imagine, for instance, that now these two cars are mangled up and traveling off with some final velocity stuck together, in which case we can say P final is equal to, now the cars, when they actually get in a wreck, clearly it's not uncommon for a window to bust and the glass to be on the road and a bumper to get ripped off. But generally speaking, the mass after the collision is going to be very, very close to the mass before the collision. So I'm going to say it's essentially 300,000 kilograms times V final. And since they stuck together, that means that their velocity will be common. So we can say that if the net external force is 0, then this will be equal to P final, which is in fact equal to 3,000 kilograms times V sub x I hat plus 3,000 kilograms times V sub y j hat. So from that, you can get that V sub x is equal to 2e to the fourth divided by 3,000, which is 6.67. And V sub y would be 6e to the fourth divided by 3,000. Crap. 6e to the fourth divided by 3,000 gives me 20 meters per second. And in fact, you could even realize that this is going off at an angle theta, such that theta equals the tangent inverse of 20.0 over 6.66, which is equal to 20 divided by 6.67. Now I'm going to take the inverse tangent of that. And I get 71.5 or 71.6 degrees. So that's a little impromptu example of how you can treat a system as opposed to a single particle. You can treat a system with Newton's second law, even in this form. And you can do it and then solve it to find out what the final velocity of the two things stuck together is. Now, it's not normally the case that you can solve it with that little information unless, like I said, they end up sticking together. So that's the beauty of conservation of momentum. A lot of times, conservation of momentum can be used to just solve collision problems. And collisions aren't always oopses where you run into each other. A collision can be, for instance, you're running on the beach, trying to pace yourself just right, because you're running to catch up with and jump on a skimboard, for instance. If you're doing that, then when you jump onto the skimboard, that is a type of collision, even though it wasn't like a car wreck or anything. But again, the net external force on the system would be zero. So conservation of momentum says the momentum before is equal to the momentum after. That's what we're shooting for here. Any questions on that? So that stuff with the cars, that was just an attempt to show you how to actually compute what two cars will be doing after a collision, and if they stick together, in fact, not only how fast they'll be going as they skid away on the road initially, because obviously friction is going to build up really quickly, but also in what direction. And because the northbound vehicle was twice as heavy as the westbound or eastbound vehicle, that's why it went basically 71.6 degrees north of east, as opposed to closer to 45. If it was two identical cars, you'd probably expect it to come more like a 45-degree angle. So that's a little bit of what we get from Newton's second law. We get the rocket equation. We get the idea of conservation of momentum. As I told you, we also find that momentum has units of kilograms times meters per second. So we don't make up any new units for that. We just keep it. You'll also see that there's another unit for that. If you realize, for instance, 1 Newton is equal to 1 kilogram meter per second squared, then you could see that a kilogram meter per second is the same thing as a Newton second. So that's another unit you could use. And I'll show you another way of dealing with that. So again, starting with Newton's second law, the summation of the forces is equal to dp dt. You can do something kind of tricky with this, and you can say the net external force multiplied by dt is equal to dp, and then you can integrate both sides of that, and what you get is something defined to be the impulse. So what you see is several different versions. So we can say impulse, and you can use I for that if you want, for instance. Impulse can be approximately equal to change in momentum, but that's also equal to the net force multiplied by delta t. But impulse, you don't have to necessarily use an approximate answer by saying impulse is equal to the integral of dp, and it's also equal to the integral of the net external force times dt. Now, if you look at this particular part, I think you'd see that the impulse has the same units as the momentum, which would make you conclude kilograms times meters per second. But if you look at this part, you'll see that impulse also has the other unit that I said a second ago, which is newtons times second. So hopefully that'll help you a little bit. Any questions on that? Okay. So let's say I'm really going to have a hard time doing this, but anyways. I have no idea that I spelled his name correctly, but Djokovic hits a serve that leaves his racket strings at 70.0 meters per second after the strings had applied a force for about 4 times 10 to the negatives. Oh, excuse me, 4 times 10 to the negative third seconds. I got ready to say 6 there. So 4 milliseconds. What is the average force? Applied. So I'm going to assume in this case that the force applied was in fact all in one dimension. So, you know, when you actually serve a tennis ball, for instance, you're doing a little pronating of the wrist so you can brush the back of it and cause it to do spin and all the stuff. We're just going to imagine you're hitting it like a hammer and take it at that. Okay. In some sense, that's still right, because ultimately the ball is going to leave in some direction nearly perpendicular to the strings. And we know it's going to have some initial speed. So what we're going to do is we're going to solve it, assuming that this is all one dimensional. So here's our solution. So with this particular solution, what we know is the summation of the forces is equal to approximately delta P over delta T. In this case, we're going to assume that, yeah, there's a lot of other forces acting on the ball. So for instance, when Djokovic throws the ball up, it's going to go up usually right very close to where it reaches its maximum height. That's roughly where a professional tennis player wants to strike the ball. It might have fallen a little bit, or it might still be on the up a little bit, but in general, we're going to assume it's at zero velocity. So we can say that force, which the racket is applying to it, it's going to be way bigger than any other forces. So the force of gravity is going to be there. Air resistance is going to be there. That's pretty much it. There might be a wind, but all those forces are minuscule compared to this force of the racket strings on the ball. So we're going to drop the idea of taking all the forces and just take the biggest one, because the other ones are so much smaller. So we'll say F is approximately equal to delta P over delta T. And in doing so, we're going to say F is equal to delta P, delta T. The delta is always final minus initial. So by the way, I'll say that the mass of a ball is equal to 0.060 kilograms. Okay. So the momentum final is 0.060 kilograms times 70.0 meters per second, minus 0.060 kilograms times the initial velocity, which we're going to say is 0 meters per second. And then all this is going to be divided by 4 times 10 to the negative third seconds. And this is going to give us 0.060 times 70 divided by 4e to the negative 3, and that gives me 1,050 newtons. And remember, a newton is approximately 0.25 pounds. So F would be about 260 pounds. Now, that's quite a bit. In fact, earlier today, I did the same calculation using 65 meters per second. And in that case, I got about 225. I don't know if you pay any attention to the NFL, but there's I think they call it a combine or something, but there's basically a series of athletic and strength tests that they push college athletes and tryout athletes for the NFL to. And one of the tests is rep out with 225, which when I used to bench press, I used to do that as well. And I think I never got more than 13 or 14 225s. A very typical but good one would be 19 or 20 reps. And if I remember correctly, several years ago, there was a guy from Virginia Tech who was a lineman, not Virginia Tech, he was a guy from Georgia Tech, excuse me, who was a lineman. And in the combine, he ended up doing something like 42 225-pound bench presses. So that's not only is that a huge leap of strength, 225 pounds is pretty heavy, but it's also a really good muscle fitness and metabolism fitness to be able to do that many before you exhaust yourself. But looking at that, imagine 225, 260 pounds. That's the kind of weight that if someone hits you with that, I mean, it could bust your skull and that sort of thing. So yeah, being hit by a tennis serve with the actual racket as opposed to the ball's going to hurt bad enough, but the racket could really do some damage. So that's kind of a neat little problem you can solve. And that also gives us a way to get an average force because you can just treat the dp/dt as a delta p delta t. Any questions on that one? And I think that's a DJOVOKOOVIC, but I apologize to Djokovic for misspelling his name because I'm pretty confident I did. But anyways, that's also the person that they have a photograph of in the 5th edition of the textbook. In the 4th edition, I think we had a picture of Andy Roddick, but now it's got Djokovic. I will tell you, just because you don't always get to talk about such things, and we don't get to cover chapter, I think it's 13, which is where fluid mechanics is. But in fluid mechanics, you'd learn that, in fact, Djokovic, when he hits a serve, often he hits what's called a kick serve. And a kick serve is when you're trying to hit the ball and you use your hand to pronate with your wrist. You pronate a little bit, and that little twist on your wrist causes the racket to not only hit the strings of the racket, to not only hit the back of the ball, it's going to hit the back of the ball in the top right side of it or quadrant of it, and it's going to brush upward. And by brushing upward, it puts topspin on the ball. So if you look at the actual ball from the side, you would see the ball like this, moving with a velocity, say, v, but in fact, it's also rotating in this direction like that. And that would be what we call topspin. So the kick serve is essentially a topspin. It's got a little side spin to it too, but the topspin part is really the critical aspect. Now remember, it's moving to the right, so air molecules are going this way. And you can sort of think of this as the air molecules that go along the bottom, they get brushed along really quickly. So you end up getting basically high speed going here. And there's something called the Bernoulli principle that says high speed implies low pressure. Now, if you look at the top, the air molecules are actually being slowed down by this. So this actually causes high pressure. Actually, I should have did that with red. That actually caused high pressure. So the ball ends up going in the downward direction. That's what topspin does. That's why it's good in ping pong. That's why it's good in pickleball, tennis. But if you also look at this as a slider and you're looking from above instead of from the left or right, if you look at it from above, then this could be a right-hander who's following through with his wrist on the inside of the ball, sort of throwing a slider. That makes the ball spin from this perspective in a clockwise fashion. Again, it's going to make a low pressure on the right and a high pressure on the left. So the ball is going to go down and to the right as the batter tries to face it. If you actually did the opposite, which is let your fingers swing around the outside like this, then you're going to spin it the opposite way. And then the ball is going to fall down into the left, which is a typical curveball. That all comes from fluid mechanics, and you'd be surprised at how little speed and rotation you have to have a huge effect. I can tell you because I slow pitch softball, playing tournaments and stuff like that for many years, and I pitch mainly because I'm good at ping pong and have quick reflexes. I don't know that I have them anymore, and I know for a fact that I can't lift my arm quick enough if someone tries to kill me, so I don't play it anymore. But to be honest with you, what I realized after doing it for a little while is if I don't pay close attention to what my fingers are doing to the spin on the ball goes all sorts of places. So when I don't pay close attention to it, or if I cross the threads versus lay my fingers along the threads, I get entirely different results. So it doesn't take much of a rotation to cause this effect. Now, one more problem I wanted to show you. And this one, we're going to imagine a water hose. So we have a water hose like this. And out pops water. And the water is moving out at a rate. And I'm going to use this symbol just because it has the right units. The water is pumping out at a rate of let's say at a rate of 2.0 kilograms per second. And let's say the water itself is moving at a velocity of 25.0 meters per second. And what it's going to do is it's going to hit the surface of your car and just come to a stop. So the water is going to go like this, and then it's going to shoot out this way. It's going to shoot out this way. It's going to shoot out this way. It's going to shoot. In other words, the velocity, at least parallel to itself, is going to quickly go to zero. What we'd like to know is what is the force due to the water. So in other words, the window is actually stopping the water, and we want to know how much force is put on it. Well, if you remember what we found was the net external force is equal to dp dt, and of course the dp dt was d by dt of mv, which gives us dm over dt times v plus m times dv dt. Well, we know the mass is actually changing and the velocity is more or less staying constant up until it hits the window. So this term is essentially zero, and all we have left is that. So I'm going to say the F is approximately equal to dm dt times v. Now, you might also, just to come across this the same way I did back when I was taking algebra-based physics class, I just saw that the units worked out, and someone asked me a question like this. So I looked at it, saw how the units worked out, did that, and got the right units, and lo and behold, luckily got the right answer. So in this case, notice it's going to be 2.0 kilograms per second times 25.0 meters per second. And that gives me 50.0 with one extra sig fig, 50.0 kilograms meters per second squared, which is 50 newtons. Now, remember, again, a newton is about a fourth of a pound. So this would be on the order of 13 pounds. Now, funny story, when my wife met my mother for the first time was when my mom, who's a very non-traditional woman who does a lot of things like roofing houses and building things and stuff like that, and, you know, working on engines and stuff like that. And technically she didn't work on engines, but she did do a lot of stuff with houses and painting and stuff like that. So she was out doing a little job where she decided, yeah, that's pretty funny. But she's also a beast of an athlete. So like she played with with a lot of women that are now in the Hall of Fame for softball in Virginia. And she also played basketball with Nancy Lieberman and some other Hall of Famers and stuff like that. So she's a really good athlete. But anyways, she was doing this odd job where she rented a pressure washer to clean someone's house, the outside of their house. And she was out doing it. She never used a pressure washer before, but she just on a whim took the pressure washer and laid it on her foot. Well, it turns out pressure washers have a lot of pressure, and she ended up literally breaking her big toe. She didn't know she broke her big toe, but she called my wife, who works in medicine, and asked her, said, "Hey, my foot's hurting. You know, you think I should do anything about it?" She said, "Yeah, that actually can break a bone. So you might want to go get that checked out." So we ended up going up to patient first, took my mom up there, took my mom in and my wife, and lo and behold, she had indeed broke her toe from the water, and also had cut it open pretty bad, so they had to stitch it up. And let me tell you, the shots they give you in your feet like that, you really need to think hard whether you'd rather have the shot or the needle without the shot, because the shot is so painful. I literally had the same shot like 3 weeks before it, and I almost punched the lady that gave it to me. So anyways, a sidebar there is to be very careful with the pressure washer. It can hurt you. Anyways, that's enough here for right now. We've covered we've covered basically everything we really need to get started. I can now go in a little deeper into chapter 9, where we can start talking about types of collisions. We're going to talk about elastic collisions, which are collisions in which kinetic energy is conserved. In addition to momentum, remember momentum, not only should you know the law of conservation of momentum, you should know exactly when momentum is conserved. So that's something that you should learn as a physics concept that you really need. It's not always conserved. There's very specific things that have to be true for it to be conserved. And then if you have the added advantage that the collision you're studying is elastic, then that means the kinetic energy is conserved. So if you're talking in 2 dimensions, you have a summation of the momentums for your system before the collision in the x direction is equal to the summation of the momentums after the collision in the x direction. So that's one equation. You have the same thing for the y direction. That's another equation. And then you have another thing where it says the summation of the kinetic energies before the collision is equal to the summation of the kinetic energies after the collision. So that's 3 equations, which allows you, of course, 3 unknowns. So that's a very important thing. We're going to do that both in 1 dimension, and then we'll go off and do it in higher dimensions as well. And we're going to derive some very general expressions for the cases of elastic collisions in 1 dimension. And by 1 dimension, I mean they're literally head on, because there's no other dimension to go to. So they can either go basically straight and completely miss, which technically couldn't happen in one dimension, or they hit head on. And when they hit head on, the one of them could be sitting still and be super heavy, in which case the lighter one's going to bounce backwards. But there's also cases where they both move off and to the right, say, when initially just one of them was moving to the right. So we're going to calculate all those different kinds of quantities. That'll go next time. I suspect we'll probably need next time and a little bit of the time after. So on Monday, we will almost finish chapter 9. And then on Wednesday, we will probably completely finish chapter 9 and jump into 10, which is rotational motion, and then 11. After 11, we'll go to 36 if possible. Otherwise, we'll just jump to 14 and 15. You folks are free to go. Let me know if you need anything. I will wait for the last person to leave in case anybody has any questions. But have a good day. Thank you for coming, everybody. Looks like that's it. Anybody else here? Oh, yeah, we got a few more people here. Anybody have any questions? I'm writing some notes so y'all see them when you download it. So perfectly inelastic collision is a case where they, like the cars that we did where they collide and then stick together. That turns out to be called perfectly inelastic, specifically because elastic collisions are when kinetic energy is conserved. But when you're in a center of mass frame for a collision, it turns out that in the center of mass frame, you follow the center of mass of the two cars, which are going like this, say. So that center of mass is doing this, but after the collision, they don't have any velocity whatsoever, so they have no kinetic energy. Hence, they call that a perfectly inelastic collision. Micah and Alyssa, do y'all have any questions? Oh, Olympic lifting.
Oh yeah, I was waiting
Yeah.
for that.
I have not actually.
Oh, okay.
A friend that holds the world record for strict curl competition.
Oh yeah, I got you. Yeah.
Yeah, if you
That's
Google
awesome.
strict curl, you'll see Arnold Schwarzenegger, and then you'll see John Cooper. And John Cooper is like a friend of mine from high school that lives
Awesome, man. Yeah.
12 miles down the road. But he's like, I think he's in like I want to say he's the 185 weight class or maybe the 205, but he curls 225 pounds. It's pretty freaking impressive. I did a lot of bench press and I didn't do much with curls, which
Oh, I
shows
got you.
my
Yeah.
biceps are all
That's cool.
crappy.
Yeah, I just started with some bodybuilding stuff, but now I just like to do powerlifting and Olympic lifting.
Mhm.
So I was watching some of those guys, I think it's around 100 kilo weight class or like 95 kilo, and they'll
Right.
be snatching like 400 pounds or something. And they start off super slow and they hang at the bottom, and then the impulse they put into it's like so much they lift it all the way over to their head, like less than a
Yeah.
second.
And they use those weird, have you seen the shirts and stuff that they wear?
Yeah.
Well, that's what
And
we do with the power bench press,
yeah.
which I did a little bit of, but yeah, my shoulders are gone to crap from it because
Yeah,
I
me
used to do
too.
25 sets of bench press a day.
Yeah. When I was training on like chest days, I did a lot of sets of like bench press, and I also
Mhm.
did incline after that. So that was like, yeah. And I did a lot of sets too. Oh, and also for inelastic collisions, I think when they stick together, it's like the work, right? There's work that keeps them together.
Yeah, I mean, you can
Yeah.
calculate the stuff that causes them to stick together, but sometimes you're actually designed to stick together. For instance, when two train cars collide forward and backwards, they have a mechanism that makes them stick together. But
Oh, I
yeah,
got you.
that are just they get mangled so much that they're stuck.
Oh, okay, that's cool. All right, thanks, Professor. I'll see you later.
Problem. Have a good one, Manka.